Appearances for the record.
Good morning, Your Honors. Catherine Forgie, F-O-R-G-I-E, for the plaintiffs.
Morning. And you want to introduce your team?
Yes, Your Honor. I've got our first witness, Dr. Beate Ritz, who's sitting there, and Pedram Esfandiari, who's sitting there, standing up, David Wool, Mike Miller.
Good morning, Your Honors.
These three are our co-leads. Robin Greenwald.
Good morning, Your Honors.
And Amy Wagstaff.
Good morning, Your Honors.
Morning.
Morning.
Morning, Your Honor. Joe Hollingsworth from Monsanto, and with me is my partner, Eric Lasker.
Good morning, Your Honors.
And to his right is John Kalis.
Good morning.
And next to John is Mimi Lynham. And behind me, sitting behind me, is my partner, Kirby Griffiths. And behind him is my partner, good morning, my partner, Heather Pigman. Thank you.
Morning. As you all can see, we have a special guest, Judge Ioana Petru from the Alameda County Superior Court. I issued a notification to all state court judges who are handling similar matters throughout the country that they were invited to participate fully in these proceedings and make these proceedings part of their record in their cases. Judge Petru is the judge who has been assigned virtually all of the California state court cases throughout the state. The cases have been coordinated in her courtroom, and so she's joining me here and will be here for the duration of the proceedings this week. The parties in her cases have stipulated that these proceedings are part of the record in those cases. So welcome, Judge Petru. Thank you for coming. We also are making these proceedings accessible to the public and to other state court judges in a couple different ways. I've told the other state court judges who couldn't make it out to San Francisco that they can listen in on the proceedings through court call. And so we've got court call up and running, and I expect that various state court judges off and on will be listening in on the proceedings. But also we're doing video recordings of the proceedings through our Cameras in the Courtroom pilot project, and both sides have consented to the recording of the proceedings. Monsanto requested that we not post the recordings until the week of hearings is done, and we will of course comply with that request. And so the video recordings of the hearings will be up either at the end of the week or the beginning of next week, and I've informed the state court judges that they can access those recordings as well. So I think that's about it. The only other thing I wanted to say to the parties, for purposes of tailoring your presentation and maybe not spending too much time on the basics, is I just want to be transparent with you about what I have read and what I have not read so far. And obviously throughout the week there will be more time to do more reading in the evening, but so far I have read every expert report. I can't promise you that I've read all the footnotes, but I've read every expert report. I've read every brief that the parties have filed. I have read the IARC monograph, including the preamble. I've not yet read the EPA reports. That's certainly one of the things on my agenda to read this week. I'm trying to think. I think. Oh, and then all the. I believe I've read all the pertinent cases on causation, or all the most important ones. So what I would ask is that you please work with your experts to tailor your presentation accordingly and presume that amount of knowledge. And of course there will be opportunity in the state court proceedings to supplement the record to the extent that it's necessary. So with that, the plaintiffs can go ahead and call their first witness.
Morning again. We'd like to call Dr. Beate Ritz to the stand, please. In your honors, as a preliminary matter, we have put together books for the judges, the clerk, and for Monsanto that contain copies of her PowerPoints, the expert reports, which I understand you already have, but they're already in the book, some slides that she's going to use, and copies of important medical studies that she'll be referring to. I think it'll make it easier for everyone. So with Your Honor's permission, I'd like to pass those up to the clerk and Your Honors and to Monsanto.
Great.
Or my partner's going to do it.
First name is Beate, B-E-A-T-E. Last name is Ritz, R-I-T-Z.
We put up the CV slide. Okay. So I did not realize that Your Honor had read all the expert reports. I appreciate that. But let me just very, very briefly go through a few of your qualifications, just because I think they're important. Can you state exactly what it is you do, please?
Yes, I'm an occupational and environmental epidemiologist. I actually am tasked by the state of California in the Center for Occupational and Environmental Health at UCLA to investigate occupational and environmental causes of disease. So it's really a discipline where we teach our students and we do research that involves assessment of workplace hazards. And my specialty has been pesticide exposure assessment over the last 25 years. I've done very large studies in the Central Valley using the California registries, the pesticide use report registries, and I've worked on many different diseases, including cancer. I'm also currently the sitting president of the International Society for Environmental Epidemiology. That is a group of individuals who professionally assess exposures, so that's how we define our tasks. And I have published more than 260 peer-reviewed papers in the area that I study, and pesticides are a big proportion of it.
Thank you, Doctor. Could we see the next slide, please? Can you explain, please, Doctor, very basically in layman's terms, what epidemiology is and some of the basic concepts of epidemiology?
Right. So I'm an MD, PhD, so I really am interested in human health. So, and the studies I do are really population-based studies, meaning we are assessing in worker cohorts in the population what hazards might be related to the outcomes, the health outcomes. So for occupational exposures, that is, we have a lot of good tools because workers and their workplaces are usually described well in terms of the agents they're using, the substances, how long they've been using it, etc. And that's one of the really important tools in epidemiology that we have. Workplace exposures to say, well, this chemical in this kind of environment with exposure over so and so long, we can now really link to an outcome, a health outcome. So what we're doing in our studies is trying to identify either hazards or protective factors that are related to human health. So my lab is really a human lab, or better, the population of California or a worker population, and we are trying to assess whether the risk of disease in those who are exposed differs from the risk of disease in those who are unexposed. And we are generating these rates, disease rates in the exposed, and then divide them by the disease rates in the unexposed. And if that ratio is 1, we know the one in the exposed isn't higher than the unexposed, right? And so what my students learn to generate are these relative risks, odds ratios. They all measure the same thing. They all measure whether in the exposed group there's more risk for the outcome than in an unexposed group that we presume is as similar as possible to the exposed group except for the exposure. And we use different tools to do that, but generally we have different study designs that we are dividing into cohort and case control studies. The only difference between the two, with one we are starting with the outcome cases, and we are selecting controls, and then the controls provide us with exposure information, assuming that the exposure information for the controls did not contribute to disease because they're controls, right? They don't have the disease. So they give us the rate of exposure among the controls, that if the rate of exposure is higher in the cases, we then can say there's a risk. In the cohort study, we go the other way. We start with people who are unexposed, who are exposed, and then we follow them over time to see what the disease rates in the two groups are, and we again calculate our ratio measures.
Thank you. Can you explain what statistical significance is and how it is used in epidemiology, please?
Yes. So statistical significance is a very complicated but easy tool in some ways. Because statisticians have made up rules of that a 0.05 is the measure of statistical significance. However, what we are teaching our students is that with p-values and statistical significance testing, we're really just assessing whether the results of our study are how they are influenced by random noise, by random error. What we also tell our students is that random error, yes, is important. We should take it into consideration, but it is really not the most important tool we have. Much more important is that we are actually assessing systematic biases. And systematic biases are confounding, selection bias, and very importantly, exposure assessment and outcome assessment that's done right, that we get the information right. So all of these other issues are more important than just getting the p-value right, but we are using statistical significance and p-values to gauge how much random error, how much random fluctuation there is in our data that contributes to what we're seeing.
And with regard to your explanation about p-values not being the be-all, end-all, do you have support for that proposition or that you can reference for the court, please?
Oh, yes. My teacher, who wrote the textbook on epidemiology, has a whole chapter, chapter 10, that I still use with my students when I teach, in which he explains why a singular p-value is really not what we should be using. We should be using the full data that's provided in a study to us. We should use confidence intervals, p-value distributions, and really assess these data to the fullest we can, and not just rely on a p-value. We actually have a t-shirt we wear in that class when we teach it that says, "No p-value allowed."
And have you read the deposition of Monsanto's, or one of Monsanto's epidemiologists, Dr. Ryder, in this case?
Yes, I've read Dr. Ryder's statements, and they completely agree with what I just said.
With regard to p-value?
With regard to the importance of p-values.
Okay.
We use them as a tool, but they are just that. They are one tool in our toolbox, and not the sharpest.
Okay. Perhaps like me. Can we go on to potential and confounding factors? Can you explain in layman's terms, please, what a potential confounding factor is and what an actual confounding factor is?
Right. So confounding refers to these biases, and it is one of the important biases we are trying to avoid. It comes from this concept of that we would want to know what would have happened to those who were exposed if we could take the exposure away from them. So would they have had the same disease risk if there hadn't been the exposure? That's, of course, a counterfactual. We can never know that for a group of people who has been exposed, or for an individual. So what we do is we construct these comparison groups. So the comparison groups are supposed to give us this counterfactual rate, the rate of disease when you're not exposed. But how do we know whether these unexposed are actually the right comparison group? Well, we know it by trying to judge whether there's potential confounding. And potential confounding comes in when really there are other underlying risk factors for the disease that the unexposed have, but not the exposed at the same degree. So that really the unexposed either are at a higher risk of the disease due to other factors, or a lower risk, right? We want to make them as similar as we can. So we assess confounding and we deal with confounding. The problem is there is potential confounding where we can argue whether a factor is really differentially distributed among the exposed and unexposed, or whether it's a risk factor. And there's actual confounding, which means in my study this applies. And for every single study, we have to really very carefully, and this is what I teach, very carefully assess whether the same factors should be considered confounders or not. Because you can actually muddy the pond by calling something a confounder that is not and putting it in a model. You might generate confounding, you might generate bias. So we need to use every single bit of information we have from prior knowledge to establish, first, is this a risk factor for the outcome? If not, it can't be a confounder. Second, is this factor also associated with, correlated with, influencing the exposure status? Those are two criteria that need to be present for confounding to happen. And the third criterion is that it's not, that the factor is not in the pathway between exposure and the outcome. So it can't be caused by the exposure and then causing the outcome. Those are the three principal components or criteria that we need to check off before we say it's a confounder. And it is different for every single study.
Lastly, can you please explain what exposure misclassification is, including what exposure is?
Right. So this is really what my discipline focuses on in occupational and environmental epidemiology. And I tell my students the one thing you need to learn is to assess exposures right. Because when we make a mistake in exposure assessment, it is the same as if we have a very noisy room and you're trying to hear my voice. You will not hear my voice, you will not see hear the signal above the noise. So if we have a lot of exposure misclassification, it's basically information bias. We have a lot of noise, and there is maybe a true signal somewhere. There is a voice in that noise that I should be discerning, but I can't hear it. So the worse I'm doing as an exposure assessor, the more likely is that I won't hear anything, that I won't find the signal. We always think it's the opposite, that we hear voices that tell us untruths, that there's a big signal that, you know, is a false signal. And what I really try to convey to my students is most of the time we have very poor instruments, our exposure assessment is no good, and if we see something, I actually get worried because I know if I do a bad job in exposure assessment, I won't see a thing. I will just drown out the signal in the noise.
And finally, can you explain the difference between retrospective and prospective?
Yes,
And how
so
it applies to cohort studies and also to case control studies, please.
Right. So retrospective and prospective is really how we generate our data. And when we talk about retrospective, then we are saying that the exposure information is in the past, and we are using tools to assess what happened in the past. The simplest example is we are asking people questions, right? And they have to remember, and they have to report. So that's a retrospective assessment. A prospective assessment is I put a little monitor on my radiation worker, and over time I follow their exposures, and I also follow them for the outcome at the same time. So I follow them for health outcomes, and I measure on a daily basis with a radiation meter their radiation exposure prospectively. Of course, we have radiation meters. We don't have any tools that can actually get us this type of information for pesticides.
Okay, great, thank you. Now let's get to the heart of the matter and talk about the relevant studies as they relate to glyphosate-based formulations and non-Hodgkin's lymphoma. So can I have that for us? Okay, first of all, can everybody see this? Is it? My screen's a little small. Okay. Can you first explain what this is, doctor, and how what it is. Just explain what it is.
Yeah, this is supposed to just be a simple visual aid. We call it a forest plot, and forest like the woods. And so really what we have in the middle, that blue line, is a stem. And that blue line reflects the null value, or the rate or odds ratio of 1, where the rate in the exposed is the same as the rate in the unexposed. So the ratio is 1, right? Same number of cases in both. So if all the red dots, which we refer to as point estimates, those red dots, if they either line up on that blue line, we would say the studies show that there's no effect. Or if these red dots fluctuate around that red line to the right and the left, we would say there's so much random noise and random variation between studies that, on average, they are null. And we can kind of guess what a summary estimate across all these studies would mean. It would mean the summary estimate would be right at having a dot right on the blue line. So then we have these lines and the whiskers, and that is what we refer to as a confidence interval. In this case, it's a 95% confidence interval, and that gives us the spread of that red dot that might be due to random error. So it's not systematic error, it's just random error evaluation. And when these whiskers are above to the right of the blue line, then they are above the 95th, then the 95th percentile is considered statistically significant. And if they go to the other side of that line, then that red dot and its confidence interval would not exclude the null, so it might indicate that there is an effect, but I cannot exclude random error. So generally what it helps us to do is see how all these red dots are actually lining up. And in this case, you can actually see that most of these red dots are to the right side. To the right side means an increased risk. To the left side, it means a decreased risk or protection. And the pattern is a nice visual to kind of gauge where most of the studies with their relative simple yes-no exposure estimate here lined up, and they lined up to the right of that blue line.
And Doctor, you teach at UCLA, University of California in Los Angeles, correct? Mm-hmm. And do you teach about forest plots and confidence intervals, and in general the epidemiological principles that you teach at UCLA, are they generally accepted in the scientific and epidemiological community?
Yes, that's exactly what I do, and we teach from the book at UCLA that my colleague actually co-wrote, Dr. Greenland, that's considered the basic textbook in epidemiology, and that I cited before with the one chapter just on p-values.
And those are the same things that you're explaining and teaching to us here in the courtroom, correct?
That's exactly it.
Okay. And I noticed that on the forest plot, there's some studies that appear to be on there twice. Do you see that?
Yes.
Can you explain why that is, please?
So sometimes it is not as easy to make a decision, because when you make a visual, you have to decide which study, and not only which study to represent, but also studies present multiple estimates, multiple dots. And you have to decide which of these dots might have the best information, the most information, and sometimes it just helps us to outline that there's more than one way to look at this data. And for example, I'm showing you the DeRuse 2005 and then also the Andreotti 2018 results, because these are major studies, and I didn't feel, even so they are on the same individuals, I didn't feel it was justified to take one out and leave the other in. It's just a foundation for a conversation about what these estimates mean.
And can you explain how the differences or the similarities between statistical significance, p-value, and confidence intervals, and how they fit on your forest plot, please? Right.
So all of these are completely mathematically aligned with each other. So these confidence intervals, the lines with the whiskers, they represent the 95% confidence interval. If those whiskers don't go across the blue line, it's statistically significant. If they cross the blue line, it's not statistically significant. However, you should not just look at the widths or where it lands, but also where the central estimate, that red dot, is. What is the direction of the effect? Because any study can be not having enough information, not having enough statistical power to exclude random error, but they can still tell you something about the direction of the effect. And that's why this is plotted in this way, because it shows you what the general direction of the effects are across all studies.
And let's look at a couple of these studies in more detail, and let's start
Before
with...
you move from the forest plot, Dr. Ritz, if I could just ask you, of these studies on the forest plot, how many of them are adjusted for exposure to other pesticides, and which ones are they?
It's a very good question. So the problem of exposure adjusting for other pesticides, actually it is the DeRusse 2003, which has the 650 next to it. That is the most highly adjusted estimate. It actually adjusts, I think, for 40-some other pesticides. And you can see that while the confidence interval could be considered wide, it still excludes the null. It's still statistically significant. And the red dot is above 2. So it's a more than twofold risk increase that's statistically significant and completely adjusted for every other pesticide. I know Anne-Claire, and I would have probably argued with her about this approach, not thinking that she should have put 40 pesticides in there, because that's not how I teach my students. I teach my students you have to really consider whether any one of these pesticides is a risk factor for the outcome. If it's not, you shouldn't put it in the model. If it is, then we can discuss whether that pesticide also is related to the one under investigation, glyphosate in this case, meaning do the two pesticides really correlate with each other, or does one imply the other is also used? And if that's not the case, then again, we should not be throwing this into the model. However, she went all out and threw them all in the model, and the effect estimate is still statistically significant.
Can I ask a clarification question about that? I think you said that you shouldn't include the pesticide in the model. You shouldn't adjust for the pesticide unless you know it's a risk factor for NHL.
Yes,
that
that's
right?
correct. That's the first rule of assessing confounding.
So, but what if you don't know whether the pesticide is a risk factor for NHL?
Right. Then we...
That in an epidemiological study?
If you don't know, you have to think about what you do when you put this. Then you would say, I want to try out what happens when I put this in my model. However, you then have, when that model then shows a different effect estimate, we have to discuss what that means. So, for example, smoking causes lung cancer. I don't think we want to argue about that, right? But somebody has a brilliant idea where they say, okay, I really think it's not smoking, it's breath mints that cause lung cancer. So let's ask everybody also whether they are chewing breath mints. And let's now say that 90% of all smokers take breath mints because they, want to get rid of that odor. And when you then say, okay, shouldn't we put breath mints? We don't know whether it causes lung cancer. Shouldn't we put it in the same model? What will happen is that the effect for smoking on lung cancer will happen. By definition, because you are now putting two highly collinear variables into the same model. Whether that means now that breath mints cause lung cancer or not, or breath mints are just an indicator, a proxy for smoking, you have to decide. So we have to decide for every single pesticide whether it is truly a risk factor for the outcome, and we should consider it as a potential confounder, or it's an indicator for having used the pesticide under consideration. It's just
So-
coming along. It's a rider.
So your opinion is that if we don't know a pesticide is a risk factor for NHL, we should not adjust for it in a study?
That's not, sorry if it came across wrong. No, I'm not saying we should not adjust for it, but when we adjust for it, we should really be careful about how we interpret what's happening to the effect estimates. Most likely is that the confidence intervals widen when you do this, and that the effect estimates, if that pesticide is highly correlated with the one under investigation, it is you who has to decide whether it means it's a confounder, it's a true risk factor, and I should adjust for it, or it's a proxy like the breast mint, right? And nobody will take that away from us. We just have to do that.
And so you mentioned DeRoos 2003. Are any of these other studies adjust for other pesticide use?
The Erickson study adjusted for other pesticides, but the estimate I'm showing here, I don't think is the adjusted one. No. So that's actually where it happened, as I recall, where when you put one or two other pesticides that are highly correlated with the actual glyphosate pesticide, then that red dot goes to the middle. It's 1.5 instead of 2.
And so why did you include a portrayal of the Erickson study on this forest plot that did not adjust for pesticides when adjustments had been made in that study for pesticides?
Right, because the pesticide they adjusted for, MCPA, was one that was used prior to glyphosate, and glyphosate was the one that followed up, that was replacing MCPA. So we have exactly a situation where you need to decide whether you believe that MCPA is a true NHL causative factor, or it's just that breast mint that tells you, well, they used MCPA, then they had a new agent that they thought was working better, glyphosate, so they replaced MCPA by glyphosate. So MCPA is just an indicator for later glyphosate use. So you have to make that decision. And I didn't see a literature that told me that MCPA was truly an NHL risk factor.
And any other studies on here adjust for other pesticides?
Yeah, DeRoos and Andreotti. DeRoos 2005 and Andreotti. Mm-hmm. AHS, yes. Mm-hmm.
What about
What about McDuffie?
McDuffie, I don't think the one I'm showing is adjusted.
So the McDuffie did adjust for pesticide use, but your portrayal of the study does not include an adjustment for pesticide use. Is that right?
Other types of pesticide, yes,
Okay.
yes.
And what about the NAP study, if I may jump in? Is that adjust for other pesticides as well?
As far as I know, yes.
That's
oh, wait,
one other.
the one I portrayed didn't, but they later showed also an adjusted one, yes.
And that shows an elevated odds ratio after you adjust for pesticides in the NAP study, correct?
Yeah, it depends. Actually, there are different ways to do this. Some authors like to just throw every pesticide in the same model, and some authors just use one after the other. And you then have to decide which estimate is the one that you want to present or you want to talk about. But they're trying it's called sensitivity analysis. They're trying out, well, what happens if? So they are sometimes using one pesticide because they think it's maybe the more convincing one that could have an effect on an NHL, and then another one because it's a common use or it's a very toxic one, and they want to see how these effect estimates change. That's actually how we're testing our data, how much changes when I do one thing or another.
So I should move this into evidence. It's Exhibit 297 on our exhibit list. And
Admitted. And have you, by the way, have the parties stipulated to the admission of all these exhibits in advance? Okay, so then if it's something that you've worked through together already, you can just do the mechanics of getting them admitted afterwards, so we don't have to spend the time doing it.
Okay. I will do that, Your Honor. Okay, so going back to the DeRusse study for a second, you mentioned that it was the most highly adjusted and that it was an elevated odds ratio and statistically significant after the adjustments. Is that correct?
Yes.
And approximately how many pesticides did the DeRusse adjust for in the, as you've indicated on the forest plot?
I understand it's some 40 plus pesticides.
And for each of these studies, did you look at and consider the methodology that was employed by the authors of the study?
Yes, definitely.
How did you go about doing that?
Well, you want to know how the study design, first of all, you ask what the study design is, but then you also want to know how the actual study was conducted. And so what you want to know is whether the disease assessment was properly done. And just about all of these studies had very high, very good disease assessment with cancer registries and pathology. So I didn't see any problem in that regard. And then, of course, the second most important thing is how the exposure was assessed. And generally, all of these studies are using interviews. None of them were able to assess biomarkers or any kind of records, except that McDuffie actually went back and asked farmers whether they could go to the suppliers and ask the suppliers about the purchasing records for pesticides, and then compared the purchases for the specific farmer and what the farmer had told them to the purchasing records. And they found that they agreed very strongly. And where they had disagreements, they were able to actually rectify the disagreements because the farmer that year had bought the pesticides somewhere else or not applied them. So that is a very nice tool to use, going back to records, but not everybody can do that. Then if it comes to interviewing, you really have to consider how the interviewing was done. Was it done in person, face-to-face? Did people go to the homes of these people, give them a chance to look at their purchasing records, spend time with their partners to discuss what they had done in what years? Or did you just give them a questionnaire that you gave them half an hour to fill out? And that makes a big difference. There are case control studies with maybe 400 cases and the same number of controls where home visits are done and these individuals report on their use of pesticides for hours in a very interactive way with the interviewer. And I would consider that a much better exposure assessment than giving somebody a sheet of paper with 20 pages and say, well, in the next 20 minutes, please report, right? So that's the way I would assess the exposure assessment in these different studies. And then the next thing is how much did they then also ask about lifestyle factors, other pesticides, other possible risk factors for the outcome, such as family history of cancer, and then how did they bring all that together in their analyses, and are the analyses done adequately with the data at hand, and then also interpreted in a sufficient way.
Let's go to the 2002 Hardell study, please. And you weren't asked a lot of questions in your deposition about specific methodology, but Monsanto has attacked the methodology of some of these studies, so I want to walk through some of the methodology in the individual studies, okay? How was the unexposed group defined in the 2002 Hardell study?
Right. So the Hardell study is one of these typical case control studies. it was a Swedish study, and Sweden, just like all the Scandinavian countries, has exceptional record systems for health records, as well as for retirement and occupational records. I actually have a large study that's NIH funded in Denmark because of that reason. We're all jealous of the Scandinavians. So they are using these beautiful record systems to identify cases, and they also have population registers from which they can pull the names and addresses of unaffected people. That's called a population-based selection of controls, very well done. And then they go and interview these people about their exposures. When it comes to the analysis, so I didn't have any problems with any of that. When it comes to the analysis, you are now asking yourself, well, what happens, because we know farmers don't just, farm one crop. Most farmers don't just farm one crop, but even if they do farm one crop, they may be using different herbicides because whatever they're the pest they are trying to get rid of, the weed, may get resistant, or they might have received recommendations to alternate different pesticides over the years to not make the weeds resistant. So generally, when you ask a farmer, they use more than one agent. It's not like in industry, like my radiation workers, where the one exposure they had was radiation. Here we have a mixture of exposures. So when we want to compare what any singular chemical does to an outcome, we have to consider the co-exposures, but we also have to consider what is the true or the correct comparison group to use. And what Hardell chose, and later Erickson as well, was to say, well, what happens if we are comparing the glyphosate or phenoxyherbicide exposed individuals to controls that did not use pesticides? So these are community studies. This is not like the AHS where everybody was a farmer who actually applied pesticides. This was done in communities. Some people were farmers, others weren't. And the critique often is that, well, you're comparing farmers with farmers. If your farmer doesn't use glyphosate, he probably used DDT, and that's also a carcinogen. So you're comparing people who are exposed to one carcinogen to people who are exposed to the other carcinogen. If you don't see anything, that's because they're all exposed to some carcinogen, right? So what they tried to do here is exclude anybody who had any pesticide exposure from the comparison group and say, now we have a clean group. We have a group of individuals who have glyphosate exposure with or without other types of exposure, but we are comparing all of them to people who never used pesticides. Sounds like a good idea, is not such a good idea. And I try to explain that to my students, because what we do when we get a little more technical, we call it a collider bias. And I explain that to my students what it is, but then I also say, well, yeah, collider bias is a kind of selection bias, and you should not generate this selection bias by excluding, in this way, people who have other types of pesticide exposure from the control group. But then I keep going and say, well, this is a potential bias, right? And they generated this potential bias. But the next step is to assess what is the quantity of that bias, because we are a quantitative science. We're not a qualitative science. We want to know how big is that bias. And now let's estimate how big that bias would be. And it's pretty simple to do in this case. All you have to do is add the controls back into the comparison group who they excluded. And they actually gave you a few tables that showed that data. And I was able to put that back in, redo the calculations, and convince myself that the change in the estimate that they are representing is within about 10% of the estimate. So the quantity of that bias is minimal in epidemiologic terms. Yes, there's bias, but it is minimal.
And I should have mentioned that the Hardell 2002 is Exhibit 20, and Hardell 1999 is Exhibit 19, and Erickson 2008 is Exhibit 17. And I will mention the exhibits beforehand. My apologies to the clerk and the court. Okay, so then let's talk about Erickson 2008 for a minute, which is Exhibit 17. Did Erickson 2008 analyze latency periods at all? And can you explain a little bit about what latency is and a little bit about the difference between latency and exposure, please?
Yes. So we are not talking about exposures that cause immediate disease or death, right? We're talking about lifelong exposures, occupational exposures that eventually, when you reach a certain age, might have contributed to your cancer. So what we are wondering is, how long does it take to initiate that cancer? And generally in cancer epidemiology, we think it might take at least a year in any single individual to have that process develop. For blood cancers, and lymphoma is a blood-related cancer, we usually think that it could be faster than for solid tumors. For solid tumors, we at least want 5 or 10 years. For blood cancers, 1 year, 2 years could be a minimum latency we want to see. And most studies actually, this included, therefore exclude any exposure that's within 1 year of diagnosis. And that makes a lot of sense. So, but the next question we ask is there like an optimal time period that I should look at for the exposures to have caused these outcomes? And is that within the last 10 years prior to the outcome? Are those exposures more important? Or are the exposures more important 10 to 20 years prior to the outcome, or even longer? And so what Erickson tried to do is find a way to say, well, what is the optimal time period of exposure? Like, was it in the 40s for these farmers that are now in their 60s? Was it in the 50s? And that's how they then tried to split up their data in these different chunks, 10 years prior to diagnosis, 10 to 20 years, 20 to 30 years, and estimated these relative risks, these risk increase measures for the outcome according to exposure that happened in those periods, with the goal to see whether, and that's another rule, if you say, well, every exposure is the same, whether it's 2 years prior to your cancer or 30 years prior to your cancer, you're probably making a mistake, right? It may be that you needed 10 years of exposure and then the first cancer cell developed, but it was killed by your immune system. You had another 5 years of exposure, the next cancer cell developed. Your immune system was weakened, that cancer cell kept going, right? So it's a process. But some of the exposures in the 20 to 30 year and maybe the 10 to 0 year might be not as important as the one in the middle, where most of that carcinogenicity really is happening. Because once that cell is initiated, you might have continued exposure because you're not diagnosed for another 10 years. But all the exposures that happen from the cell being initiated to you being diagnosed are irrelevant because they haven't, the cell is already there. So those exposures are not contributing anymore. So when I add irrelevant exposure to relevant exposure, the same thing happens. I'm muddying the pond. And I'm estimating relative risks that are smaller. So in order to actually come closest to the truth, I want to find the optimal period of exposure. And that's what Erickson tried to do here. And they found that the optimal period of exposure prior to the outcome was probably somewhere in their data between 10 and 20 years prior to diagnosis. However, it is interesting when you read this closely, the last 10 years had almost no exposure. So they didn't say that, but I interpreted this as if these farmers had stopped farming or stopped using herbicides. They had absolutely no phenoxy herbicide exposure anymore, therefore they couldn't even estimate exposure in that period, and they had very little glyphosate. Therefore, the estimate for glyphosate had a huge confidence interval. And the huge confidence interval gives it away. There must have been very little exposure to estimate anything.
And with regard to Erickson 2008, which is Exhibit 17, Monsanto has been arguing that the 1.1 odds ratio, which is almost a null, is the most reliable odds ratio for glyphosate-based formulations because it was observed during the 1 to 10 year latency period that you just discussed when there were no cases for exposure to other pesticides in that period, and thus no confounding. Do you agree with that position? And if you don't, can you explain?
Absolutely not. I really think they had no statistical power to estimate anything in that period, and that's what that wide confidence interval around the point estimate for glyphosate reflects. I really think that these farmers had stopped farming, and therefore there was no more exposure. So how do I estimate anything in a period when nobody is using, most people are not using herbicides anymore? That data just isn't there. I can't estimate it. I need to go to a different study that actually has that kind of data.
The data is not actually there to make that determination.
I think the estimate tells you there's no data there to estimate anything for that period.
Okay. Again, in Exhibit 17, which is the 2008 Erickson study, is there a meaningful difference between the odds ratio for greater than 10 days of use versus the odds ratio for less than 10 days of use?
Yes, actually I really like what they did here in terms of trying to get to some kind of dose response. So the days of use, that no use at all, 1 to 10 days of use, more than 10 days of use, are getting at, is there actually, and what I'm seeing here is not reflecting what I'm talking about. Yes, there we see it. So we are seeing that compared to those who never, in Erickson, never used glyphosate, there are 12 cases who report 1 to 10 days per year use. So it's not 1 to 10 days, it's 1 to 10 days per year on average, because they were asked to report their average use. And then you can see that that estimate is somewhere between 1 and 2. The red dot, the point, is probably around 1.7 from what I see. And you can see that the lines and the whiskers are wide, and the left one actually includes the 1, meaning that 1.7 is not, I cannot guarantee that there isn't random error that produced this estimate, right? The confidence interval includes the 1. However, the next estimate, more than 10 days per year, is greater than 2. It's probably around 2.3, maybe. And you can see those confidence intervals are not crossing the 1, right? So that's a statistically significant 2.3, I can't remember, 2 point something estimate for more than 10 days per year use. What I really like about it is you're not supposed to just say, is this statistically significant or not? You are actually supposed to now say, well, when I go from less than 10 days per year to more than 10 days per year, do I see some kind of pattern? And that's also how I teach my students. Do we see patterns in the estimates? I see a pattern. I see a dose-response pattern here. Even so, statistically, for the one estimate, I cannot exclude random error.
So this slide here is part of Exhibit 297, as are all the slides, but I'll reference them all as 297 from now on, which I hope will help the court and the clerk. So with regard to this slide, can you explain what this is and what it's trying to show, and also explain in more detail, please, what dose response is and how it affects your opinions with regard to causation?
Right. So these are authors who actually tried to get at a dose response. And McDuffie is very nice because they distinguished between less than 2 days, or 2 and 1 day per year, and more than 2 day per year use of glyphosate. Pretty much what they are saying is it's not just a yes-no question whether glyphosate causes NHL, but it's a question of whether you are an occasional user, you spray a day, right, here and there, or whether you are potentially a routine user, more than 2 days per year. Every year, you might be spraying 3, 4, 5 days. And you can clearly see here that distinguishing the routine users, the users who have a common use pattern, for them you see that that red dot is really above 2. And you also see that the 95% confidence interval excludes the null value. It's statistically significant, as I would expect if there's a dose response or that higher exposure should be causing the disease at a higher rate. And I don't see anything for the occasional users. So it tells me occasional use might be okay, but don't use this routinely. And the estimate is more than twofold. So your risk increases more than twofold if you're a routine user.
And what does that tell you with regard to your opinions about causation?
Well, this was definitely part of how my opinion was formed, going for patterns, going for dose response in studies that I considered very strong, and McDuffie and Erickson belong to those kind of studies. And so does the NAP study, which is actually a compilation of the North American and the Canadian study. McDuffie is a Canadian study. Erickson.
Sorry to interrupt. Before you get to the NAP study, could I ask one more question about the Erickson study?
Please.
There was a slide that flashed across the screen before this one that was not the slide you were looking for, but it mentioned multivariate analysis and univariate analysis.
Yes.
Can you explain to me the difference between those two things and
Yes.
what and how that relates to Erickson? What is portrayed
Right.
in the in this slide with respect to Erickson?
Thanks for asking. It actually makes my point. And the point is so the left, the univariate column, shows you the relative odds ratios, which are representing relative risk ratios here, for the pesticides that were found to be linked to NHL in this study. They investigated a lot more, but these are the ones where the relative risks actually indicated an increase. And you can see that these authors are actually very thorough. They are not just showing you...
Just to clarify, this is Erickson?
Yes.
Okay.
This is Erickson. So they're not just showing you the Swedish study. They're not just showing you the ones where, it's statistically significant, but they're showing you every estimate that is above 1 because they want to say, well, if we want to be health protective, we should consider any estimate that's probably above 1.5, and they actually state that in their paper, because a 50% increase in NHL risk is something we should be worried about. And statistical significance is not all, because a larger study may show that it becomes statistically significant. So they're showing you these estimates from 2.8 to 1.61. And you see for glyphosate, it's 2.02. And here it's statistically significant in a univariate analysis, because that the confidence interval is 1.10, the lower one, it's above 1. So that says it's statistically significant, it's a twofold risk increase, but here we only put glyphosate in the model. That's univariate, one variable, one risk factor at a time. And then the multivariate, they threw them all together in the model. Okay, all of the ones that you see here, tar, creosote, arsenic, a known tar, creosote, arsenic, mercurial seed dressing, glyphosate, 2,4,5-T and 2,4-D, MCPA. So the MCPA and 2,4,5-T, 2,4-D are phenoxyherbicides. They are the old herbicides we used in the 60s. Actually, 2,4,5-T is famous for having dioxin contamination in Vietnam War, right? So glyphosate is the next one. And when you put all of these together in the model, you can see on the right side under multivariate what's happening. All of these odds ratios shrink, right? They go towards 1. They're smaller. And all of the confidence intervals widen and now pass the null value. This is exactly what I said when I talked about confounding. If you put multiple variables into the model that are correlated, and they are actually explaining that MCPA, the phenoxy, was taken off use in Sweden and replaced by glyphosate. This is what you expect to see. It doesn't mean that the true estimate is 1.5 instead of 2 for glyphosate. It just means my statistical model is behaving in this way because I put highly correlated factors in the same model. So I'm measuring the same thing 5 times in the same person. I just don't have enough information to do this correctly, because what you would want is a large group of people only MCPA exposed, only glyphosate exposed, only tar exposed. You don't get that, right? And that's why this pattern occurs. And it also occurs in every single one. And you can see that arsenic now looks like it has no effect, and it's a known carcinogen. It was 1.6 before, now it's 1.17, right? But again, it's because arsenic is actually one of the very, it's one of these inert ingredients that's in a lot of the formulations. So it's probably the highest correlated with all of what they're doing here. And that's what I expect if it's the highest correlated, because it's in many different formulations. You know, I can't estimate its singular effect anymore. I can't when I do a multivariate. And that's the drawback of these kind of analyses. It's just what we live with. And we need to know how to interpret this.
Okay. With regard to the McDuffie 2001 case, which is Exhibit 21, Monsanto has argued that the data, that there's issues with the data, or that it's somehow flawed because someone with 20 days cumulative exposure may be placed in the low exposed category, while someone with 3 days cumulative exposure may be placed in the high exposed category.
Right.
Comment on that, please.
Right. With every dose scale I invent, I can make mistakes. This could be one mistake. I could be placing some people who are cumulatively much more high exposed into the group that's the low exposed, and the opposite. But you see what happens when I do that? I misclassify information. And again, we are back to the noise to signal ratio. In the end, if this is non-differential, meaning I'm doing it for cases in the same way I'm doing it for controls, not differential by case status, we call it non-differential exposure misclassification. What we get in the end is we don't see anything. So if this really happened, then I would be worried that the effect estimate I'm having on my screen here is not high enough, because I introduced a shrinkage towards the 1.
You consider, again, or did you consider that the lowest exposure group in the DeRoos 2005 AHS study includes individuals who could be categorized in the highest exposure groups in both the 2001 McDuffie study, which is Exhibit 21, and the 2008 Erickson study, which is Exhibit 17.
Again, we use, it's correct if you want to say it this way. However, we have different scales here that we are comparing. We are comparing an average of 10 days per year to a cumulative of 20 days in my life. An average of more than 10 days per year could mean 50 days, 100 days, we don't know, right? Because they just grouped it in one group. So to make these general statements of, oh, the highest and the lowest across studies is not really justified. You have to really go into the data and compare the exposures. Also, I told you before that I'm concerned about the relevant exposure period, right? If somebody had all of his exposures 2 years before being diagnosed, it could be 200 days because he decided to want to be a pesticide applicator or to introduce GMO crops, right, and spray heavily every single day. Those 200 days could be completely irrelevant to the NHL because they were 2 years before, while somebody else had 30 years of regular application 3 times a year. and he may not reach the 200 days, right? So these are issues we really need to consider. What is the right time period? What is the right number of days? Is it cumulative? Is it really that I every year I'm doing this? Or is it that I have 5 very intense days of spraying, I get my cell damaged, and from then on, I can spray whatever I want. It doesn't matter anymore. That one cell is starting to be a cancer, right?
Is there anything else with regard to either of these two forest plots in Exhibit 297 that you want to explain further?
The only thing is that the NAP study really is combining the North American studies that DeRusse 2003 published on and some of the McDuffie data, and that it is a powerful pooled study, meaning they got all the data together to do these analyses. And why it's powerful is that they were not only able to assess NHL as one big category, they were able to now also look at certain subtypes of lymphoma. And you see those listed here as follicular lymphoma, large B-cell lymphoma, and other lymphomas. And they're showing that basically all of these have an increased risk due to glyphosate. It's not just one subtype of lymphoma. And they also show that actually the overall estimated effect here for the routine users, right, not the occasional users, the routine more than 2 days per year users is way above 2. Okay, and statistically significant.
Okay, with regard to the NAP study, has that been presented as a poster or an abstract, or in other words, do we have the complete study? And can you explain how the NAP has been peer-reviewed, please?
Right. So the NAP study has an abstract that was submitted to the ISAE conference. I'm the current sitting president of that society. And I was many years on the committee, scientific advisory committee, for reviewing abstracts for conferences. And I know that we make a big effort to review every single abstract for its scientific validity, and we get a lot more abstracts than we can accept every year. So yes, they are reviewed. However, they are abstracts. They are not a full paper. I also reviewed for this the slides that were shown at the conference. And so I had personally the opportunity to actually see the analysis and the data that they presented. And that's partially what we are showing here.
And I should have mentioned that NAP is Exhibit 301. Okay. Can we go back to the to the original forest plot, please? Okay, and you mentioned earlier in your testimony, Dr. Ritz, that and you can see this, that most of the red dots, the odds ratios, are to the right of the study, and then there's to the right of the blue line, the one, and there's a few on the left, notably the agricultural health study. Is that correct?
That's correct.
Okay, and what is the method, when you have something like this where most of your forest plot is to the right of one and just a few to the left, is there an epidemiological methodology that you use and that you teach your students as to how to analyze this situation? Right.
Yes, there is. So it actually points to a qualitative difference, right? So we're interested in quantitative differences and qualitative differences. And when we really see that one study seems to estimate different effects from all others, we have to ask ourselves, what is the qualitative difference between these studies? And here it's pretty simple. All the other studies are case control studies. The egg health study is a cohort, right? And generally, egg health study is a cohort. Sorry. So generally, we would hope that a cohort study is of very high quality, and it's collecting data prospectively. It might be avoiding biases that otherwise we might be concerned about. However, the way I also teach my students is we cannot just judge a study by the design. A case control study well done has as much, if not more, information sometimes as a cohort study. We are conducting case control studies for a very good reason. We are conducting them because diseases are rare, and cancers are rare. We don't usually think about them that way, but they are. So to assemble a large number of cases takes us a lot of time. A cohort study needs to be 50 to 100,000 people if you want to assess cancers. Any cohort study that's smaller will have to follow individuals for 50 years to get any kind of number that makes sense to look at for cancers, especially for rare cancers. So cohorts are a challenge for cancer, and everybody knows that. The early cohorts were cardiovascular disease cohorts because almost every second person develops cardiovascular disease, and that's easy to study in a cohort. Cancer cohorts are extremely difficult because they have to be so large. Since they have to be so large, they're costly. They're very expensive, and they're not only expensive in terms of money, they are also expensive in the time commitment you need from the individuals. Because you have to not only enroll them, you have to be able to follow them over time, right? You have to be able to recontact them. You have to be able to find out what happened to them after enrollment, not just at enrollment. What kind of exposures did they have after enrollment? What kind of diseases did they develop? The nice and good thing about the Ag Health study, they knew that they could do what we call a passive follow-up. Passive follow-up is, we have a cancer registry. As long as we can run all the names of the cohort members across the cancer registry, we will find those cancers, right? We never have to talk to the farmers again. We'll find their outcome passively. Good design for that reason. The problem is, and the Ag Health study is different from the most famous cohort study in the US, the Nurses' Health study that Hubbard's is running. The Hubbard study recontacts these nurses, 120,000, since the 70s, every 2 years. They are asking every 2 years what these nurses are doing, okay? And they're updating the exposure information every 2 years because things change. Whether women take estrogens changes, whether we take aspirin as prescribed changes. There are lots of things that change. We change smoking behavior, right? We change diet. We change pesticide use, right? So the problem and the beauty and the challenge of a cohort study of pesticide application is not only how do I assess the pesticides that the farmers used in the past with a questionnaire and do that accurately, how do I then also document how that exposure over time changes, right? And that is the big challenge in the Ag Health study that I think the Ag Health study really struggled with, because the second time, it took them 5 years in the early 90s and mid-90s to do their baseline assessment. And by the time they were done with that, they realized they needed to update the exposure because there was quite a lot of pesticide use changing, specifically and most dramatically the glyphosate use. So they started, not because of glyphosate, but in general, because, you know, a good investigator does that. They want to go back and see whether things change and how they change. So they tried to find these farmers again between 1999 and 2005. And they found 63%, 38%, a third of all farmers.
I think it was 37.
37, yeah. Good. Yeah, a third, 36.6, whatever, 37. Didn't want to be found, had died, didn't want to answer, couldn't be found, had given up farming, or didn't want to talk to the researchers anymore, right? Didn't have time to talk to the researchers. So now we have a cohort in whom and by the way, the beauty of the Nurses' Health study, these nurses are health professionals. That's why Harvard was so smart to start that cohort, right? Because they are committed. They are absolutely committed individuals. Over 90% have been followed for 30 years. right? That's different from after 5 years having lost 37% of your cohort, right? So these farmers, when they enrolled, weren't really sure they wanted to be in this cohort. They were given a questionnaire at a pesticide licensing exam. Some of them might not even have been sure that they wanted to fill it out, but were worried that maybe I don't get my license if I don't fill it out, right? And then they go home and say, well, that was it for me. I'm not going to answer any more questions. And that is actually also documented in the large percent of people who were given an additional questionnaire to take home and fill out and never send it back in, right? So these cohort members were not as committed as the nurses, and my colleague who was my chair for a long time always, he is the initiator of the Danish birth cohort of 100,000 babies, and he always said, if in doubt, stay out. You do not want a cohort you cannot follow, okay? You need to get committed cohort members because you want to ask them again because things change and you need to update exposure, you need to update a lot of different things about these people.
Okay, Doctor, looking at this slide, the disadvantage of the cohort method, and
Right.
the following slide, which is the agricultural health study as an example of cohort, those two slides, which are both part of Exhibit 297, where did those two slides come from?
They are from my slide deck that I use in the core epidemiology teaching class that I teach every single year, and I've been teaching for 20 years. And these slides are PDFs that I found from 2012.
So these two slides talking about the disadvantages of the cohort methods and using the agricultural health study cohort as an example of that are from a 2012 teaching slide that you prepared long before you got involved as an expert in this litigation. Is that correct?
That's correct, because I like to use practical examples when I teach my students. And I was an advisor for a while on the egg health study, so I knew it quite well.
As an advisor to the
Yes,
agricultural
as an
health study.
advisor.
Okay. And let me turn to, hold on. Well, why don't you tell me, please, what are some of the issues that you saw in the agricultural health study other than the 37% that did not return the second questionnaire?
Right. So the issues, I think it's a beautiful study. I really admire my colleagues for doing it, and I think there's a very big amount of useful data that they produced, and I congratulate them to this wonderful study. However, there are disadvantages of a cohort, and these disadvantages unfortunately hit this study very hard when it comes to glyphosate. And that is the disadvantage of having to update your exposure. But it's also the disadvantage of pesticide research in general, because we do not have the radiation badge for pesticides, right? So the only thing we can go from is recall. We have to go and interview these people, and we have to ask them to report what they used. And we can do, and I do that in my studies, we can help people with visuals. We can help them by saying, well, go back and look at your purchasing records. Could you ask your wife? Could you ask your son? Do you know who, purchased this with you? Can you reconstruct your exposure history? Because it's really like archaeology. We are trying to reconstruct an exposure history for these people. The Egg Health study, having to enroll 56,000 applicators because they wanted to follow them prospectively for a rare outcome. They only had 575 NHL over 20 years and 56,000, right? It's not a huge number. The case control study started with 500 cases. So if you want to do that, you have to have an instrument that people won't just give back to you and say, I'm not going to do this, sorry, I don't have the time. 56,000 people have to fill out 20-some pages within half an hour telling you, reconstructing their own exposure history, doing that archaeology on the spot. And that is challenging. And, you know, I really admire my colleagues for believing in their instruments and doing it, but everybody knows, and it has been documented and discussed again and again, what you get are failures in memory, failures in reporting, right? And we see here, this is how they asked it. This was a bubbling questionnaire. So we have Roundup, the pesticide. Have you ever personally mixed or applied? Yes, no, easy. But then how many years have you personally mixed or applied? And you have categories, oh, well, maybe 10 to 20 years. Okay. And then in an average year, how many days did you apply? So you have to say, okay, 10 to 20 years, what was my average year? Is that the last year? Because most people remember things that are closer, better than things that were further in the past. And maybe they report just that last year. And it's really not the average year, right? So you're challenging people to do a lot of complex archaeology of their exposure history on the spot when they're there to get their pesticide applicator license. And glyphosate at the time was not sold to them as a highly toxic pesticide, right? They had concerns about pesticides other than glyphosate that might actually cause acute symptoms. And the farmers probably experienced acute symptoms from pesticides such as organophosphates. Organophosphates are derived from sarin gas. Organophosphates give you flu-like symptoms, right? So somebody who comes to get this licensing done for restricted use pesticides and then is asked about 22 different pesticides will probably remember the most important pesticides they have in their mind because they're toxic and they really want to avoid exposures. They want to really get the application right. More than one they kind of think is, you know, something that I give to my wife to go and spray the weeds in the yard, right? And so it's about the attitude of reporting. It's about being encouraged to report correctly and even to remember or weigh these things correctly.
And with regard, I should mention that this this questionnaire for the agricultural health study has a separate exhibit number, which is 228. And then with regard to, can you explain how many questionnaires were used in the agricultural health study? And can you explain it in light of what exposure misclassification is? And does the exposure misclassification and the recall error apply to not just the 37% that responded to the second questionnaire, but also to the 63% that did not respond? I mean, yeah.
Right. So what we have in front of us here is actually the baseline questionnaire, because the second time around, those 63%, they were interviewed. And that questionnaire was very different. It was a telephone interview, right? And there were prompts from an interviewer. By the way, it really helps to have prompts from an interviewer. This is really the quick and dirty, I call it, one that you give to people and say, fill it out, right? You're here for your licensing exam, just do it. And you get it back, and the data is the data, and you live with it. What happens when you do that is you generate potential recall error. Recall error is not recall bias. Recall error is something that I just misremember, misreport, you know, it's not systematic. Recall bias is systematic. Because I'm a case, I'm remembering differently. Because I'm not a case, I remember differently. This is random error of recalling or reporting. The problem is this is really the enemy of exposure assessment in a big way when this is about protecting public health, because it causes non-differential exposure misclassification, a randomness in the exposure misclassification that is that signal to noise ratio reduction. So you will not find a signal. You cannot protect the public if you don't see anything. And if this reporting is done wrong and you have it, you know, whether you develop the disease or not, doesn't matter. It was just a random error. The non-differential misclassification of that exposure makes it likely you don't see anything.
I've been having a hard, that's one of the things I've been having a hard time understanding. That concept comes up in a number of the reports and the supplemental reports on the AHS study.
Right.
This concept of non-differential exposure misclassification moving us closer to the null, no matter what.
Right.
And I'm just having a hard time wrapping my head around that. I was wondering if you could explain why that is the case in a little more detail.
Yes, and you're not alone, believe me. My students have the same problem. And I show them lots of examples, and you know, they finally develop an intuition when we do the numbers. But the easiest way to understand it is that when you have random error, you're moving people, let's say it's just exposed, unexposed, right? And somebody forgot that they used glyphosate, so they're not reporting it, so you're putting them in the unexposed group. And somebody else misread it and thought he was using glyphosate, but it was really a different agent, and you put him in the exposed category, right? So you're moving some people from the exposed to the unexposed, and randomly some people from the unexposed to the exposed. So in essence, you're minimizing the difference that that you can see in disease rates because you have contaminated both groups with the other. That's it. Make sense? Good.
And does this idea of non-differential exposure misclassification, is that something that people have been aware of and published about with regard to the agricultural health study?
Absolutely. So there are many people who are, of course, in my field aware of this. We all are. But there's actually specifically groups who've been addressing this with respect to the agricultural health study. And the first one we list here is de Grey et al. In the federal government's agricultural health study critical review, which was from the Harvard Risk Assessment Group. It's a distinguished group of scientists who were charged and paid by CropLife, which is an industry, pesticide industry group that issues these calls and pays for them to evaluate potential problems with the whole ag health study in general, because, I mean, it's a study that costs a lot of resources and money, and the government is conducting it, so we should be knowing what the issues might be. And they prominently state here, non-differential exposure misclassification, the one I just described, will produce bias towards the null, right? Misclassification reduces the power of the study to detect any genuine cause-effect relationship and will also reduce the validity of the findings. That's them. Indeed, Dr. Acquavella, a colleague who I met myself when I was on the panel, on the Ag Health panel several times, and also in Los Angeles. He's a colleague who now works in Los Angeles. He was the epidemiologist for Monsanto, and he would come to meetings, present on behalf of Monsanto, and in the journal Epidemiology, which is actually the official organ of the International Society for Environmental Epidemiology, so our journal, my society's journal, we hold it in high esteem. And it's not easy to get published in this journal, and he to his credit, he did. And he wrote about exposure misclassification in the Ag Health pesticide study and insights comparing biomonitoring studies with what the Ag Health study did in terms of interviewing. And his conclusion here was that there would be, especially for that cumulative day of use measure, right? That very important one where we are thinking we can now have a dose in the Ag Health study, that would have probably substantial exposure misclassification issues, because we might assign these doses in the wrong way. And what I just explained to you was just two exposures, not exposed, exposed, happens also when we have a scale. because all of this can go in either way, in either direction, right? And so we are muddying the pond multiple times. He said it. And then we have Weichenthal. He's a Canadian colleague who reviewed all of the egg health cancer publications in 2010. He published in Environmental Health Perspectives, which is actually the official journal of the National Institute of Environmental Health Sciences. Again, very hard to get into that journal. And in this review, he assessed all of the different cancer outcomes across different studies, across different cancers, across different pesticides, and then came to his conclusion. And that conclusion also was exposure misclassification undoubtedly had an impact on AHS findings reported to date. And the next sentence, unfortunately, isn't on here, but he refers back to non-differential exposure misclassification being one of the enemies we have to be aware of.
And did the authors of the recent AHS publication, the lead author being Dr. Andreotti, and the exhibit number is 12, did they also talk about exposure misclassification?
Indeed. As any good epidemiologist should do, we list the limitations of our study, and Andreotti just the same, list non-differential exposure misclassification as one possibility to explain what they are presenting. So despite the specific information provided by the applicators about the use of glyphosate, some misclassification of exposure undoubtedly occurred. Given the prospective design, however, any misclassification should be non-differential and lead to an attenuated risk estimate.
And did, I'm going to have to move it along just a little quicker because we have some time constraints here. Did the authors of this study, they were obviously aware because of these peer-reviewed publications and their own comments, the agricultural health study investigators, did they make any attempt through either sensitivity analysis or validation studies to correct these? And can you explain very briefly what sensitivity analysis is and what validation studies are?
Right. So sensitivity analysis is really just playing with the data you have. You're not generating new data. You're just looking at your data in different ways to try to figure out whether you can assess the strengths of a bias, right? Whether you can maybe remove a bias or can argue that if I look at my data this way and this is still consistent, does that mean something?
Is that all post hoc analysis?
Post hoc, yes. And honestly, when it comes to exposure misclassification, it's really hard to do that post hoc. What we really want to do, and to draw conclusions from that, what we really want to do is go out there and measure, and then have a gold standard of measurement against which we then can judge what the exposure assessment was like. And I have to say, to the credit of my colleagues, they spent a lot of money and effort trying to do that. They had NIOSH go out there and monitor farmers in the way they were applying pesticides and then collecting urine samples from them. Dr. Acquavella himself got Monsanto to pay for one of such studies where he went out there and had observers observe farmers in the field spraying glyphosate, taking urine samples, measuring what's in there, having them fill out the same questionnaires that the Egg Health study used, and then comparing them. And lo and behold, what they found is that the correlations were so-so. They weren't too bad, but they really depended on the kind of agent. And unfortunately for glyphosate, they didn't have much luck. They had much better luck with chlorpyrifos and 2,4-D, where the correlations between the urinary levels and what they actually observed and what the observers reported and what the applicator themselves reported, those were 0.5, not so bad, but really the correlations with the urine samples for glyphosate were pretty minimal. And you have to remember, these are also people reporting within a few days of applying, so their memory is much better. They also have been observed, meaning they tried their best, right? Their best behavior. So what they are reporting is really short term. It is the best we can do, but it certainly does not tell us whether somebody reporting their glyphosate use for 10 or 20 years in the past at baseline is really reflected in that validity assessment with the urine samples.
And did can you explain a little bit about the change of use in glyphosate that occurred during the agricultural health study and how that ties in with exposure misclassification, please?
Right. So what I can do when I cannot interview people is make informed guesses. And that's what my colleagues did. They said, all right, maybe I can use the baseline information I collected, no matter whether it was good information or bad information, whether they misremembered already in the beginning or reported quite accurately. I use that data and what I know about these people to predict their future exposure.
Let me just interrupt for a second. I should say this is Exhibit 299. It's actually from the recent December 12th, 2017 EPA draft analysis with regard to glyphosate.
Right.
Okay, sorry, doctor, go ahead.
So what we see here is a beautiful map of the U.S. showing the estimated agricultural glyphosate use in 1994. The date is very important because 1994 is kind of in the middle of that baseline assessment from the egg health study. And you can you see Iowa? It's near the Great Lakes up there in the middle, and it has kind of an orangey and slightly reddish color. So that was the glyphosate use. We see that most people use, or most farms are covered, meaning they're already using glyphosate, and that's before GMO, okay? And in North Carolina, which is on the right, there's not so much use, but Iowa is definitely covered. However, now compare that, and this is the data we're using, what they report in the baseline, to then predict what they did the next 10 years, the next 20 years, if they did not answer again. This is what we see in 2014. The cancer assessment in the AHS, the last cancer was recorded in 2013 from the Andreotti paper. So between 1994 and 2014, we pretty much cannot distinguish unexposed from exposed anymore, because somehow every farmer must be using glyphosate, and not only using it, but using it at a very high level, right? This is kind of interesting in epidemiology, because we also know that as soon as a exposure becomes ubiquitous, it's really hard to estimate what it does. Because if everybody is exposed, we are now having to distinguish the amount of exposure very carefully in order to say whether the rates of disease are increasing. And so so in 2014, Iowa, we would probably be it would not even be possible to estimate any risk from glyphosate anymore. It's like with cell phones. Once everybody uses a cell phone, we cannot estimate the risk from cell phone use on brain damage anymore, if there's any. So it's the same. Ubiquitous exposure are really a scourge of our discipline. And but why I showed this is more to say, really, we are going from 1994 to 2014, trying to estimate not only the amount they are using, while everybody is starting to use glyphosate as if it's, aspirin, and we should be using it with our breakfast cereal. It is also they are trying to estimate when this happened, right? Because I told you, it is important when exposure happens, not only whether it happens. Did it happen within a year or two before the NHL? Did it happen 5 years earlier? When was that change? When did that exposure happen? And all of that is estimated for that 37%. Not only that, in the second round, they are asking farmers to now report what they used. And you would think, oh, they asked them to report what they used since we asked them first, right? That would be logical. No, they didn't ask that. They asked them to report what they used in the last year they farmed. Okay. Now I have 1 year of exposure, from which I then extrapolate for the 63% that answered. I now have to extrapolate backward to their first question and forward into the future, whether that 1 year definitely represents the 20-year period. Again, we are guessing.
Is it possible to give an example, given that there's only 1 year of information for the 37%, I mean for the percentage that answered the questionnaire, is there any way to estimate or to know how much use they actually had?
Well, we can do our best to try that, but we are ending up estimating. We can definitely predict well whether or not somebody used it, right? If they tell you they used soybeans or corn, it's probably GMO, it's probably glyphosate. How much they used, how many days they used, that's a totally different guess, right? But I have to make that guess in order to get the dose response.
Given your explanations with regard to the sensitivity analysis attempts and the validation attempts to correct the problems with the AHS study, did you make a determination as to how much weight, in your opinions, to give the AHS study? And then is there a methodological reason for the amount of weight that you gave the study?
Right. So in my scientific assessment, the exposure assessment issues were so grave that for glyphosate, which changed mid-baseline, which wasn't updated properly and had really 100-fold increases in the time period we are studying, where we're making so many guesses, I really have to downweigh the importance of the AHS study that otherwise I really love. But for a time-varying exposure, I just cannot take this study serious in terms of the science that it produced if it shows no effect, because all of the effects are drowned out in the noise of exposure assessment, exposure misclassification.
Let me go to one other issue, and can we turn to the slide that talks about protective equipment?
Mm-hmm.
Yes, this one. Can you explain, this is again from the questionnaire, which is exhibit 299? 298, sorry. 228. I'll get it right yet, the third time. Sorry, 228? Okay, exhibit 228. Can you explain what this protective equipment from the AHS questionnaire, what it is and what it tells you about the study and about how they try to do the intensive weighting scores?
So this is a very important question, because a lot of what they call their validation studies were actually trying to see whether this information tells them something about the intensity of the exposure a farmer might have gotten, right? If I use a full moon suit, I'm probably protected. If I sit in a tractor with a cab that has a negative airflow, I'm probably protected. I can spray as many glyphosate as I want. I won't breathe it. I won't, get it on my skin. I'm fine. If I use aprons and face shields, I don't get it splashed in my eyes. If I don't repair equipment, I don't have it on my hands. I don't, eat by accident without washing my hands. So we really want to get to people telling us what they do and how they do it, because that may really determine much more than the acreage or the days they sprayed, how much exposure they got. And my colleagues got that right. You should ask that, right? However, because they only had probably 20 minutes, half an hour with every individual, they did not put this question after every pesticide. They put this question at the end of the list of 20-some pesticides that they asked about. And now they said, what type of protective equipment do you generally wear when you personally handle? This is for all pesticides. These are guys who are coming to get their license for restricted use. And of course, they're thinking about the most toxic pesticide they're handling, right? And they want to say that they're doing this correctly. So what they're reporting here is not, and I really don't think it is, what they would be doing when they're spraying glyphosate. This is what they're using to protect themselves from the most toxic agent they've been reporting on. However, this question is used for every single pesticide in the same way, with the same algorithm that Dr. Dosemecki describes in his intensity of application algorithm, where we use weighing factors for having used chemically resistant gloves, for disposable clothing, for face shields, to downweigh the exposure reported for any pesticide, including glyphosate. But we don't know whether they did any of them. They sprayed glyphosate. It might have been, the pesticide that they're reporting on. We don't know.
And how is the algorithm used to determine intensity-weighted scores in the agricultural health study?
Well, it plays a big role for the intensity-weighted score. That's what that score is all about. We are weighing according to how was the pesticide applied. Did you fix the equipment? Did you wear a face shield? Whenever that question is answered yes, you downgrade the exposure. So you put somebody in the low exposed group when they're reporting that. If they're not reporting it, you keep them in the high, right? So you could see all sorts of scenarios where the true exposure for glyphosate, somebody who really is highly exposed landed in the low exposed group, somebody who was low exposed landed in the high, because they weren't reporting for glyphosate, they were reporting for any other pesticide.
Monsanto is claiming that you're criticizing this now and did in your deposition as a litigation expert, that you're criticizing the use of this algorithm, but you use the same intensity score in your work. Can you explain that?
Yes, because these really work depending on what pesticide we are talking about, right? Because that's what they actually showed in their validation study. For chlorpyrifos, it worked, right? And so we use what we know for the things that we think it works with. However, you need to ask this for each and every pesticide. You can't just generalize it across every pesticide they reported. And yes, it is an algorithm we should be using, but we should be asking these questions for every single pesticide.
Okay. Can you explain briefly what a meta-analysis is and how it relates to glyphosate-based formulations and non-Hodgkin's lymphoma, please?
Before you get into that, let me ask if you think now would be a good time. We've been going for about, I think, like an hour and 45 minutes or something. Would now be a good time to take a lunch break? And
I would love a break.
Okay.
Any kind.
All right.